All right, so we are on to our next step of curve sketching, which is we looked at our first day there of looking at levels or intervals of increasing and decreasing. We're going to do that same thing today, only we're going to take it a step further by using those critical numbers that we found that were turning points for when your graph could change from increasing to decreasing or vice versa. And we're going to use those critical numbers to look and find our high points and our low points of some function, a max or min, or another way of saying it, a local extrema, which includes both max and min. Now, a critical number of f of x is a number in which not only does the derivative equal to 0, and this is something we didn't talk about, the second part is it's also where your derivative is undefined, something is happening there. All right, so now when moving left to right through our x values, as you do when you look at a graph, if the derivative, and this is something I mentioned last class, changes sign from negative to positive at some value of c, then f of x has a minimum at this point. So for instance, here's our value where we have a minimum. And if our derivative is negative, which means our function is decreasing, and then it switches to positive, which means it's increasing, well, then that means you have a bottom or a min at that blue point. So again, over on this left-hand side, before the blue dot, before x equals c, our derivative there is negative. And then it switches after that blue dot, the derivative switches to positive. And so again, that is why we have a minimum value. And again, at that c value, well, that's the spot, and this is why it's important, that our tangent is horizontal, and so our derivative is equal to 0 at that spot. Now we got the flip side of things, where if the derivative changes sign from positive to negative at some c value, then the function has a maximum at that point. So again, your derivative is positive, which means your function is increasing. Then it switches to negative at that blue dot, which is c, and so your function is now decreasing. And so that is why we would have a max at that spot. So again, at the blue dot, in both scenarios, your derivative is actually equal to 0. And again, over on the right here, our derivative is negative, so it's decreasing. And over on the left, it is positive, which means it's increasing. Now, that's when we're talking about our derivative being equal to 0. What about that other case when our derivative is undefined? Well, again, a critical number produced by when your derivative is undefined can result in 3 different situations. The first one is what we call a cusp. So I have some graph. I'll draw one of these for all of these. A nice axis. And a cusp looks like something like this. And so at that point, right here where you're undefined, your tangent could have several different slopes. And so that's why our derivative is undefined in that spot. All right, so that's one area we could have, a cusp. And again, a cusp could look like this as well. See, an upside down cusp. Let me see here. So there's 2 different cusps, just like a vertical tangent. You could have a vertical tangent that looks like this. And so at this straight vertical line here, your derivative would be undefined because you do not have a run for a slope. You have a rise, or a drop in this case. Again, another vertical tangent could go the other way. And then lastly, something that we have talked about in advanced functions anyways, is you could have some vertical asymptote. And so your function would neither have a max or min at that vertical asymptote because it's, again, your function is undefined at that spot. So again, there's several different options of what could happen in terms of when your derivative is undefined. All right, now, example 1. For the function y equals negative x to the fourth plus 8x cubed minus 18x squared, determine all critical numbers and determine whether each of these values of x gives a local max, a local min, or neither for the function. All right, so again, the first thing I want to do is find the derivative because we need our critical numbers, and we're going to have to find our derivative and set it equal to 0. And so let's see here. So I'll bring the 4 down, find the derivative here. I get negative 4 x cubed plus, let's see here, 3 times 8 is 24 x squared. And then the derivative of negative 18x squared, 2 times 18 is 36, and knock one off the exponent. We have an x. All right, so now again, the next step for finding critical numbers is I'm going to set my derivative equal to 0. All right, and so I've got, let's see here, 0 is equal to negative 4x cubed plus 24x squared minus 36. Now I'm seeing some common factors here, so I'm going to at least try to factor this function so I can get some values. I know that 4 goes into all of them, and they're also an x. They have a 4 in common and an x in common. And in fact, because I have a 4 here and a negative 4, I'm going to factor out a negative 4x. And so my first term here would be x squared. That might help me for factoring. Divide 24 by negative 4, I'd get negative 6. Take an x out, and I'm going to get a positive 9 here. All right, so there we go. I just common factored a negative 4x. Now I've got a nice little quadratic here in brackets, so I'm going to try to factor it. So I'm going to, again, use my chart method, x squared here and 9 here. Anytime it's x squared, it's going to be x and an x. 9. I'm going to go with a negative 3 and a negative 3. So when I cross multiply again, I get negative 3x plus a negative 3x. That gives me my minus 6x. All right, so I've got my equation fully factored, where I've got negative 4x is one factor. The other factor is x minus 3, and then the other factor is also x minus 3. All right, so now I need to solve each piece. Only 2 of the pieces are identical, and the piece that makes, or the number that makes x minus 3 is 0 is x equals 3. Would make both of these pieces equal to 0, and then whatever makes negative 4x equal to 0, well, x would be 0. So there is 2 critical numbers. Now here's the extra step that we're doing today that we didn't do when we were looking at increasing and decreasing functions, or the increasing and decreasing intervals of functions. We were also looking for when the derivative is undefined. But in this case, we don't even have a denominator. That's what you're looking for. And so f of x is always defined. So we get no extra critical numbers. All right, that's the only difference today from the other day, was we're going to get extra critical numbers if our derivative is undefined at a spot. All right, but we do have 2 critical numbers, 0 and 3. So just like I did the other day, I'm going to make a table or chart. All right, so I have my number line. Again, sometimes I do a chart, sometimes I do a line. We've got 2 numbers. We've got x equals 3 and 0. So there's x equals 0. And our derivative is 0 at that spot. And we also have x equals 3. And the reason I'm putting these zeros here is because now we can have it undefined. And that'll tell us whether we have an asymptote, tangent, or cusp. But that's for later. We'll get to that. All right, so we got 3 different intervals we're worried about here. We're worried about x is less than 0. All right, that's one spot we're going to check out the derivative. The other is when 0 is, or x is between 0 and 3. All right, and then our last interval here is when x is greater than 3. Okay, so now I'm going to test my derivative here. You can use the big polynomial here. I like to use when it gets fully factored. I find is the easiest, right here. All right, and so let's see here. I put in a number less than 0, so I'm going to go with negative 1. So in my first part, negative 4x, I put a negative 1 in there. It's going to be positive. Then I put a negative 1 in here for in x minus 3. It's going to be negative 4, so it's going to be negative. Same in the other spot. And so if I have a positive times a negative, it's going to be a negative answer. But then times the negative, it's going to be positive. And so I end up with, is that right? Negative, yeah, negative 1 minus 3. Okay, and negative 1 times negative 4. Yeah, okay, so it would be positive. All right, so our function is increasing there. We'll get to that though. And now between 0 and 3, again, if I plug in a number, let's see here, like 1. So put a 1 in for the first part. I'm going to get a negative part. 1 minus 3 is also negative. And then 1 minus 3 again would be negative. So negative times a negative is positive. Times a negative again would be negative. And so our derivative, looking at my note here, it looks like I messed my note up online, but in case you're following along, it's negative. All right, and the last part, x is greater than 3. Again, I'm going to plug in a 3 here. Negative 4 times 3 is negative. Then times 4 minus 3 is positive. Times a 4 minus 3 also positive. All right, so negative times a positive is negative. Times a positive, negative. And so what I'm looking for is a change. And we go from positive to negative at 0, but then at 3, we just go from negative to negative. So nothing happens there. But at positive means our function is increasing. Then at x equals 0, it starts to decrease. And so we are going to have a max at x equals 0. And I can find out what that max is by subbing into my equation here, my original equation, which is pretty easy because every time I put a 0 in for x, I'm going to get 0. And so, whoops, f of 0 is equal to 0. Again, that's plugging into the original function. And so, therefore, there is a max, or a local max. That's not even, it's the max, actually. At x equals 0 of 0. There we go. I think I got that opposite on my note, which is crazy. I don't know what I was doing there, but anyways. All right. Now let's try another one here. Try to throw some different examples at you. For the function x cubed, determine all critical numbers. Determine whether each of these values of x gives a local max, local min, or neither. All right, so once again, I'm going to find my derivative. Same steps here. All right, and this one's easy. It's just bring the 3 down. We get 3x squared. All right, then of course the next step here is to set our derivative equal to 0. And let's see here, we end up with, 0 is equal to 3x squared. And the only way that 3x squared is equal to 0 is if x equals 0. So there's our one critical number. Then I look to see, is my derivative undefined? Nope. So our derivative is always defined. So we get no critical numbers from there. All right, well, now I'm going to make my chart like I did before. I've only got one number to worry about here. and that's x equals 0. All right, and our derivative, it's equal to 0 at that spot, and so I'm worried about two different intervals. All right, so I'm worried about x is less than 0. Oops. Less than 0, and x is greater than 0. All right, so now I'm going to test out my derivative. Well, my derivative is just 3x squared. So I put a negative number in there, like negative 1. Well, negative 1 squared is 1. Times 3 is positive. And so my derivative is positive there. Its function's increasing. I go for greater than 0, so I'll try a 1 again. A 1 instead of negative 1. And 1 squared is 1. And times 3 is 3. Again, it is positive. And so my function is increasing and then keeps increasing. And because there's no change, there is no max or min. Neither. We don't have any of them. And if you're familiar with this graph of x cubed, again, I wanted to pick a graph that maybe you are familiar with because we did touch on this graph in advanced functions. It looks like this. There we go, something like that. So it's just constantly increasing. There's no top or bottom there for this particular one. All right, next up. For the function f of x is equal to x minus 5 to the power of 2/3, determine all critical numbers and determine whether each of the values, same thing as usual, let's find a max or a min. All right, or if they don't happen, they don't happen. All right, so I'm going to take the derivative once again. All right, so I bring my fraction down, my exponent down, which is 2/3. All right, then I have my function there, x minus 5, and subtract 1 from the denominator, or from the exponent, sorry. So 2/3 minus 1 is negative 1/3. All right, now I'm going to rewrite that derivative. All right, so I've got what I'm going to have. I'm going to have a 2 in the numerator. All right, and then 3 in the denominator. And now I'm going to flip this function, that's to the power of negative 1/3. I'm going to put that in the denominator. So I have this x minus 5. So that takes care of the negative 1 because I made a positive 1, but we are taking the third root. That's what that 1/3 means, the third root of x minus 5. All right, now, just like I did before, I'm going to set our derivative equal to 0, but 2 is the numerator. And again, when we're looking to set our derivative equal to 0, we're just worried about the numerator. And because 2 is the numerator, well, therefore, f prime of x is never 0, or never equal to 0. So we don't have any critical numbers from doing that. But f of x is undefined, because now we're looking at when is the denominator equal to 0. Well, if I put a 5 in here, 5 minus 5 is 0, and then our derivative is undefined. So, but f of x is undefined at x equals 5, which means our derivative is not differentiable at x equals 5. Can't find the derivative there. It means something, there's no tangent line at that point. But something's happening, and we're going to figure that out. All right, so again, I'm going to draw my chart where we just have one value, and that's x equals 5. All right, so I'm going to look at two intervals here. We're going to look at when x is less than 5 and when x is greater than 5. All right, so let's see here. All right, we look at our values here, and so let's check it out. I'm going to have to sub in a number less than 5. Well, our derivative of less than 5, we don't even get a value. It's undefined at x less than 5. So our function doesn't even exist at that spot. And greater than 5, if I plug in a number, like, I don't know, I want to get a 9, so I'd try 14, because 14 minus 5 would give you 9. Oh no, I'd get a bigger number. The bottom line is here, though, when you take the third root of a number that's greater than 5, the number's going to be positive. And so our derivative is positive here. This is a weird situation. I've totally messed up my note on this that I have online. I'm going to totally fix that. It's totally wrong. Do that today. And it's positive there. And so, again, because we don't have a switch, there is no max or min at that spot. And actually, I lied about this undefined spot here. Man, I gotta mess this up. Hold on. Because it's a third root here, we can have a negative, or we can have a number, we can have a negative number there. Like, if I did, so I gotta fix this. Hold on here, folks. It's not undefined because I forgot here, it's a third root. And so if I put in like a -3, I would get -8. And the third root of -8 is -2. And so actually our derivative here is negative at this spot. It's actually both. But we don't have a max or min here. We get messed up here. No, it would be negative. No matter what, it's negative. What am I talking about? All right, so now when you have a negative switching to a positive, but here's a difference here in this spot, is that it is undifferentiable at that spot. So we don't have a min here because it is undifferentiable here. So we have one of those three weird cases going on. And in fact, because, let's see, I'll get to our original here, and this is something we're going to talk about more closely, is that because our original function is defined, it's not going to be a vertical asymptote. That's something we're going to look at next class. So it's got to be one of these situations, a vertical tangent or a horizontal tangent, or a cusp. It's one of these. Now our function, this is something we're going to get into more. We're just looking at whether we have a max or min here, and we don't, because again, it's because our critical number is undifferentiable. All right, it's because it's undefined at that spot, but it goes from negative to positive. And here's how we can figure out which situation we have. It goes from negative to positive, so it switches signs here. And so if it goes from negative to positive, you're going to have a cusp. And in fact, I got the wrong cusp on here, and I'll explain why. It's because it's going to go from negative slope down to positive. Now the bottom cusp here is positive to negative. How do I know it's not a vertical tangent? Because this vertical tangent goes from negative to negative. This vertical tangent goes from positive to positive. So what we're looking for, or what we have here, is this situation. And again, it's because my critical number was found because our derivative was undefined. And again, our other situation here is that we're going to deal with is when your original function is undefined at that number. Then you know you got yourself a vertical asymptote. So again, there's all these situations, but in this situation we had a cusp, not a vertical tangent. Again, that's because the signs changed. But the bottom line is for this class, for this particular lesson, is that we don't have a max or min there because we found our critical number from our derivative being undefined.